What influences fatigue? What influences fatigue is the geometry and the material and the loads. For the most part, we control the geometry and the material. The loads, if it's a customer, it can be, hard to control the customers. So there's generally more variation in loads. Material and geometry, we control that. So the material and geometry and loads all feed into the Goodman diagram. We're going to use the material and geometry to define our go, no-go area, and we're going to do the loads to see where we're at. And we're going to use a factor of safety analysis. Some people call it a design margin. Old school was factor of safety. So here we got it. Our processing is amplitude mean, and we're having an endurance limit, and that endurance limit can sometimes be adjusted in fatigue analysis for certain things. So what we're going to do is, this is our SN curve or our Wöhler curve. We're going to take this limit and we're going to develop a Goodman diagram, also called a Hague diagram. And this is going to have mean stress on the x-axis. So this is positive mean, this is negative mean, tension, compression, and this is the stress amplitude. So we're going to plot the mean versus the amplitude. Okay, basically we're going to start with the yield envelope. So we're going to take this Hague diagram and we're going to draw a point from the yield point on the y, or the alternating, to the yield point on the x-axis, or the mean. We're going to have a load here, and we're going to take the range and the mean of that load, and we're going to plot that on our diagram. Now, we know that the endurance limit is obviously below the yield point, so we're not quite there yet. We got to do some more work on this diagram. So then we're going to plot the endurance limit on the y-axis, and we're going to draw a line to the ultimate. This is called the Goodman line. Now we have an area on the tension side that is good to go. So the idea here is that if our plot of our mean and our amplitude lie in this area, we should be good to go. Now, on the compression side, some companies will change this area. This is just the base theory. So compression generally helps for fatigue. So some people may continue with this slope up. Some people are conservative and just draw it over here. Some people may even go this way, draw the line symmetric. Typically, compression helps us for fatigue. In this case, we just drew the line straight. So we got a little bit bigger area over here than there. So compression generally helps us. Now we're going to calculate how far that point is from our failure envelope. So this line, we're going to calculate this, and we're going to develop a factor of safety. So just the green line divided by the pink line. And if it gets to 1, it means we're touching, and that's not good. And sometimes people will say, okay, it needs to be 1.5 or something like that, whatever your company standard is. This is companies can design it different ways, but it kind of works the same way. We're going to use this diagram. We're going to develop a no-go area. We're going to calculate a factor of safety or a design margin, and we're going to look at those design margins for each of our loading conditions. If it's an engine, we may do an engine map, bunch of speed torque points. Sometimes, besides a factor of safety, you may see a safety margin, and that's basically just the difference in stress of this line right here. So it's this distance right here is the safety margin. Here brings it all together. There are different correction types, different theories. We talked about this Goodman line. So from the endurance limit to the ultimate strength on the mean axis. But there's other lines as well that can be drawn.